much, Judy.
Wasn't paying attention.
So, are there any questions? So we still can't talk about the test because Sarah hasn't taken it. Is she the last one to take
But
it?
I've heard there's not a take home in Amari.
I know there's not a take home. Even though Jordan thought there was a take home.
No, I did not.
So, where did we end up in our discussions on Wednesday? Seems like forever ago that we talked about this.
We
Did we
talked.
just finish the Q cycle?
We talked about cytochrome C.
So we've got the cytochrome C, so we're to the cytochrome C oxidase?
I think so.
Is that where we're going to agree that's where we are?
Cytochrome C only carries one electron.
Right, cytochrome C only carries one electron.
And you wrote the little equation on the board.
They
For
need to
the,
Like 4 electrons
Oh.
for hydrogen.
so we were balancing that equation, right?
Yeah.
So it ended up that when we balanced that, it took 4 cytochrome C with an electron, right? To reduce 1 oxygen, meaning we had to also include 4 hydrogen ions. And I think I'm going to do it again, so I will move down a level. And what are we going to get? We'll get 4 cytochrome C in its normal state, plus 2 water molecules, right? What's the matter? That looked like Melanie was thinking about that. Are we good?
Yeah.
They hardly ever show this stoichiometry. I was reading another book this morning, just sort of refreshing myself, making sure I wasn't missing something. And they had written on their figure that with no attempt at stoichiometry at all, right? This is a chemistry class, so when stoichiometry matters, we need to pay attention to it, right? So it's 4 cytochrome C, right, to provide enough electrons to reduce 1 molecule of oxygen to 2 molecules of water, okay? Does that make sense? Any questions about that? Now, this has a couple of consequences. Where is the reduction of oxygen occurring? On the matrix side, right? So this is occurring on the matrix side. So oxygen is being reduced to water. This figure does show the stoichiometry, that is half a mole of oxygen plus 2 hydrogen ions going to 1 mole of water. Right, so they've got this balanced equation cut in half. So they're at least trying to address the stoichiometry on that figure. But these are hydrogen ions that are where? Robbie? On the matrix side, which were free in the matrix, but now are part of a water molecule. So that tends to, even though hydrogen ions aren't moved across the membrane like they are as a result of complex 1, like they are as a result of the Q cycle, right? Even though hydrogen ions aren't physically moved across the membrane, this reaction still acts to reduce the concentration of hydrogen ions on the matrix side by reacting them with something and sort of using them up. So this reaction still contributes to formation of the gradient, not by acting as an active transporter of hydrogen ions like we do here and here, but by reacting with hydrogen ions that appear only on the matrix side of the membrane and thereby reducing the concentration of hydrogen ions in the matrix. Does that make sense? Okay? And this is kind of important because I used to do a calculation. Did we do the calculation when we did pH in Chem 1, in Biochem 1? Did I do the calculation of how many hydrogen ions would there be in the in a mitochondrion? Was that part of the problem set that I gave you? Nobody remembers whether they did that. I used to give a problem where I would give the approximate dimensions of a mitochondrion, and you would have to figure out the volume of that mitochondrion from the approximate dimensions. It's not bad. You assume it's a cylinder, so you can find the dimensions, how to find the volume of the cylinder. And even if I made it have round ends, you take, right, you find the volume of a sphere, split that sphere in half, and then find the volume of the cylinder between, and you can approximate the volume of a mitochondrion. So I would have students figure out the volume of a mitochondrion, and then I would have them figure out the hydrogen ion concentration from the pH. So if you assume a fairly neutral pH of like 7.4. And my question was, how many hydrogen ions would there be free within the volume of that mitochondrion at that given pH? And I think the pH I would use was usually 7 or 7.4, depending on my mood at the time, right? Now, how many free hydrogen ions do you think there are within a mitochondrion at that kind of pH? A lot? You're going with a lot? Jordan? It's kind of a fun calculation to do. What? You don't think?
Was that? There was a question like that on
Yeah,
the exam that you
was
said
it-
like never mind.
Circle C.
But you gave us the answer.
Yeah, you
No. That was a different.
Okay.
That was a different question.
Years.
No, la.
Wait, if you give them the answer, why don't I?
You will
It's
get the
on
answer.
there.
You'll know the question when you read it.
Something.
Yeah, because
Yeah.
I read it the first time. I was like,
Oh, just kidding.
you're like, oh crap. You're like, I don't know.
Right, and then you read the rest of the question and go, oh, okay.
I just found this interesting. I love it.
So, if you look at an individual mitochondria, depending on the assumptions you make about the size, how you calculate the size, what you assume about the pH, you get somewhere in the range of 8 to 15 hydrogen ions. Right? Now that's not 8 to 15 millimoles of hydrogen ions. That's 8 to 15 free hydrogen ions in the whole mitochondria. Melanie's giving me a look that says, that's true. So when we're talking about a process that moves 4 and 2 to 4, depending on how you calculate the stoichiometry of the Q cycle, hydrogen ions, and then removes 2 hydrogen ions from the matrix as the result of a reaction, when there's only somewhere between 8 and 15 free, you're changing the pH within that mitochondrion substantially. Right? You're moving a good number of the available hydrogen ions out of the matrix. And thereby creating a fairly large gradient. I mean, you're moving, you're cutting the concentration of hydrogen ions somewhere between, to at least half of its original concentration, maybe as low as 1/10 of its original concentration. Yeah?
So when you said there are 8 to 15 hydrogen ions present, is that in the mitochondrial matrix or in the entire mitochondria? Like
Well, that's in the whole volume of the mitochondrion. So if you're counting some of that as intermembrane space, the number in the matrix is going to be even less than that. Yeah. And a big part of the volume of the mitochondrion is membrane. So the amount of that mitochondrion that's actually aqueous is much less than the volume you calculate. So it's probably even less than this. So when we're talking about moving hydrogen ions, we're talking about making a really big difference in the concentration of what's available. Right? I mean, you know, when you start thinking of it in that terms, we're used to, this is one of those times when we're used to thinking about concentrations in terms of large volumes approaching a liter. And we're used to thinking of, when we talk about the amount of something in there, you know, even something that is like 1 nanomolar, which is 10 to the minus 9th molar. Well, 10 to the minus 9th times 10 to the 23rd still gives us 10 to the 14th. So that's still, if we said something, if we had a liter of a solution that had a concentration in the nanomolar range, that's still 600 trillion particles in that solution, right? We're used to thinking about processes being averaged over this large number of particles. When we start thinking about the mitochondrion, we're really, for the first time in what we've done in chemistry, we're talking about individual hydrogen ions, right? That's a real change in focus in the way we think about a process. It sort of gets back to the way we tended to try to think about processes in general chemistry, but we couldn't because we were really averaging those processes over large numbers of molecules. Here we're not, we're averaging these processes over a number of hydrogen ions we can count on our fingers and toes. That's not something we're used to doing when we're talking about chemistry. Right? That's pretty slick, yeah. Right? Changes our perspective just a little bit. Does that make sense? So, through this whole process, what was the point? We're creating a hydrogen ion gradient, right? So we created a hydrogen ion gradient. Right? So we've got a membrane separating a space. We've got more hydrogen ions outside the membrane than we have inside the membrane. I mean, interestingly, moving the hydrogen ions, remember, this intermembrane space compartment is in equilibrium with the whole volume of the cytoplasm. So it's not that this concentration changes very much, because the hydrogen ions we move across essentially are diluted in the whole volume of the cytoplasm. Where we get the big difference in energy is by reducing the concentration of hydrogen ions inside the membrane. Right? That's where that small number of hydrogen ions plays a big role. Everyone was thinking about that.
I was just thinking, like, how quickly can this happen if